Imagine this: humanity's most famous telescope, the Hubble Space Telescope, ignores the distant galaxies, star nurseries, and black holes it was built to study, and instead swivels around to gaze back at its home planet. The question comes up more often than you'd think: if Hubble aimed at Earth, how detailed would the pictures be? Could it zoom in close enough to read a street sign? Could it see you sitting at your desk? Or is there some hidden limitation that makes the idea impossible? This is the exact question posed by Kyle, and it's one that Hubble operators hear frequently. In fact, NASA's FAQ even dedicates a section to answering it. Many assume the obstacle is brightness, that Earth would be too dazzling, too reflective for Hubble's sensitive optics. After all, the telescope is designed to capture faint glimmers of ancient starlight billions of light years away. Pointing it at something as nearby and luminous as Earth must surely overwhelm its instruments, right? Surprisingly, that's not the real problem. Astronomer Phil Plait, the voice behind Bad Astronomy, explains that Hubble does point at Earth from time to time. It uses our planet as a calibration tool for one of its instruments. If brightness were the central issue, this wouldn't be possible. The real limitation is something less obvious but far more insurmountable. Hubble is simply too slow. Before we dive into the motion problem, let's talk about resolution, the raw sharpness of Hubble's vision. The telescope is the most powerful visible light observatory ever launched. It has captured images of galaxies so far away that their light has been traveling toward us since before Earth even formed. But even Hubble has limits. Think about Pluto, the former ninth planet orbiting at the edge of the Kuiper Belt. Before NASA's New Horizons spacecraft arrived in 2015, our best views of Pluto came from Hubble. And those images, frankly, weren't great. Pluto appeared as little more than a fuzzy disk, a slightly brighter blur against the darkness of space. That's because Pluto's size and distance put it right at the boundary of Hubble's resolving power. So if Pluto was already a blur, what would happen if we pointed Hubble at something much closer, like a desk sitting on Earth? In theory, Hubble's enormous mirror and optics could capture remarkable detail. At its maximum resolution, it might just about be able to distinguish a person moving around on that desk chair. It wouldn't be able to zoom in far enough to read text on a notebook or catch the expression on your face. But large-scale shapes and motions might be visible. But all of this assumes Hubble can hold the image steady long enough to take a picture. And that's where the real problem begins. Hubble orbits Earth at a blistering speed of about 7.5 kilometers per second. That's over 27,000 kilometers per hour. From its vantage point 540 kilometers above the surface, the ground below whips past in a blur. Imagine trying to take a picture of the highway directly beneath your car while driving at freeway speeds. Even if your camera had incredible resolution, the result would smear into indistinguishable streaks. For Hubble, it's the same. From its perspective, that desk you want to photograph is racing by at thousands of meters per second. Any exposure longer than a split second would result in catastrophic blur. The sharper the telescope, the more pronounced the blur becomes, because even the tiniest motion translates into dramatic smearing across its sensitive detectors. So, while Hubble can in theory resolve small details, it can't keep them still in its field of view long enough to capture a clear image. You might wonder why not just rotate Hubble to follow the ground beneath it. After all, the telescope constantly swivels to follow stars and galaxies across the sky. Couldn't it simply do the same for Earth? Here's the catch. Hubble's tracking system was designed for extremely distant objects, not nearby ones. Its automated guidance algorithms can comfortably lock onto targets at about 10 times the distance to the Moon. Anything closer, and the system begins to fail, even photographing the Moon itself. A target astronomers occasionally attempt is tricky. To pull it off, controllers have to manually override the system. They rotate the telescope maneuver and fire the camera at just the right moment. The results are interesting, better than what you'd see with the naked eye, but they're far from the crisp cosmic images Hubble is famous for. Now imagine trying the same trick for an object on Earth's surface. Relative to Hubble, your desk would sweep across its field of view far faster than the Moon does. The telescope would need to spin at about 1/10 of a revolution per minute to track it smoothly. That might not sound like much, less than the speed of a slow-turning carousel, but for Hubble it's too fast. Its gyroscopes and stabilizers simply weren't designed for this kind of rotation. At those speeds, vibrations ripple through its structure, ruining image quality. Worse, the telescope's maximum rotation rate is only a few degrees per minute, comparable to the motion of a clock's minute hand. That's nowhere near fast enough to keep up with Earth's surface rushing below. In short, Hubble can swivel to track galaxies crawling across the heavens, but not a desk zooming beneath it. Let's say, purely hypothetically, that we retrofitted Hubble with a brand new targeting system. Its rotational inertia is actually comparable to a small carnival ride, a carousel or playground merry-go-round. Not impossible to move, just cumbersome. With enough engineering, we could add thrusters, gimbals, or stabilizers that would let the telescope swing fast enough to follow Earth's surface precisely. If we did this, the results would finally approach Hubble's theoretical limits. The telescope could, in principle, take sharp photographs of features on Earth, comparable to the kind of high-resolution images you've seen from spy satellites. It wouldn't be able to read over your shoulder, but it could absolutely watch you wheel around on your office chair, walk across a football field, or drive a car down a road. But at this point, our thought experiment stops being hypothetical, because in practice, we already have telescopes just like this. Here's the twist: while Hubble itself was never built to spy on Earth, military reconnaissance satellites were. In fact, it's widely believed that the US Hubble spy satellite series shares a very similar design to Hubble. Both use mirrors of nearly the same size, both have comparable optical performance, and both are operated in orbit around Earth. The main difference: spy satellites are built with the ability to track fast, moving ground targets. So if you're imagining what Hubble could see if it pointed at Earth, you don't have to wonder too hard. The answer is already circling above us. While the exact capabilities of modern reconnaissance satellites are classified, leaks and declassified reports suggest resolution sharp enough to distinguish objects just a few inches across. These satellites can read license plates, identify aircraft, and spot individual vehicles. So yes, a Hubble-class telescope could absolutely take stunning images of the Earth's surface, just not the one we currently have in orbit for science. The question then becomes, why not let Hubble do double duty? Why can't NASA just turn it downward occasionally for a bonus round of Earth observation? The answer is partly technical and partly political. Technically, we've already covered the reasons Hubble wasn't built to rotate quickly, stabilize against vibration, or follow moving targets near Earth. Retrofitting it would require major modifications, and the telescope is already delicate after decades in orbit. Politically, NASA's charter is civilian. Hubble was built to advance human knowledge about the universe, not to conduct surveillance. Handing it over for reconnaissance would cross ethical and jurisdictional lines. That's why the US maintains two separate fleets of orbiting observatories: civilian scientific telescopes like Hubble and classified military telescopes built for imaging Earth. So, circling back to Kyle's original question, what if we aimed the Hubble telescope at Earth? The answer is a mix of yes and no. Yes, Hubble's optics are powerful enough that it could, in theory, resolve human-scale features on the ground. But no, in practice, it cannot hold those features still long enough to take a picture. The blur caused by its orbital speed and its sluggish rotation system renders the images nearly useless. To overcome this, you'd need to redesign the telescope with an entirely different guidance and tracking system, essentially transforming it into a reconnaissance satellite. And in fact, such satellites already exist, using very similar technology to Hubble. So, while the idea of pointing Hubble at Earth is fun to imagine, the reality is that we don't need to, because the US government already has Hubble's Earth tracking cousins in orbit, doing that very job. In the end, Hubble was never meant to look down. Its destiny has always been to look out, away from the noise and clutter of our atmosphere, toward the grandest scales of the universe. It has shown us galaxies colliding, nebulae glowing, stars forming, and light that left its source before life on Earth began. That's what Hubble was built for, and that's why it continues to inspire all 3 decades after launch. If you want sharp, close-up views of Earth's surface, you don't need Hubble. You already have Google Earth, countless weather satellites, and yes, classified recon satellites watching from above. But if you want to glimpse the deep past of the cosmos, to see the fingerprints of creation written in starlight, then Hubble is still our window to the universe. So, could Hubble see you sitting at your desk? Not quite. But it can show you where you came from, and perhaps, in a way, where we're all headed.